Alright, in this video we study inhomogeneous differential equations of this form. Here f of d is the polynomial of differential operator. This is a polynomial. And this is some function of x. So let's start. When this function q is constantly equal to 0, then this is just a homogeneous differential equation, and we already know how to solve this. So let's assume this is non-zero. Now, if this f of t, this polynomial, can be factorized into two factors, g and h, then we can rewrite this differential equation using these factors. So that would be g of d and followed by h of d and y equal to q of x. Then let this part be another function z, h of d, y, and substitute this into here. Then we have another apparently simpler differential equation. Okay, so here's one differential equation and here's another differential equation. So that means if we solve this differential equation first, which is supposedly simpler than the original differential equation because this factor is simpler than the original f of d. Then after solving this for, solve this for the function z of x. Then substitute this z into here and solve for y. H of d, y equal to z of x. Then we can solve for y and for y of x. In this way, we can solve the original differential equation in two steps. First this and then this. So that's the basic strategy for solving this inhomogeneous linear differential equations. So ultimately, if we just keep factorizing, we end up with something like this: d minus alpha y equal to some function. So we just keep solving this type of differential first order differential equations, and that can be readily solved by using the method of variation of parameters, which we already learned somewhere. And for this, the solution would be given as this: exponential of alpha x and integral of exponential of negative alpha x times q of x, so this function, and dx plus constant. So this is the general solution of this equation. Then we just keep solving this form of equations one at a time. Okay, let's see an example. Let's try to solve this differential equation: y double prime y prime minus 6y equals to cosine x. Then from the left hand side here, we have this polynomial, t squared plus t minus 6, which is factorized as, let's see, t minus 2, t plus 3. Okay, so we solve this differential equation. Y equals to cosine x. So let this part be equal to z. So let z equal to d plus 3y. Then the equation is d minus 2 z cosine x. And for this inhomogeneous differential equation, we have the special solution as z equal to, so from here we have exponential of 2x integrate exponential of negative 2x and cosine x dx. So if you carry out this integral, then well, I think you need to apply integral by parts twice, and the result should be, you need to check this. So negative 2 over 5 cosine x plus 1 over 5 sine x. Now let's go back to this equation. So since z is this, okay, d plus 3y equals to this function. And we solve this. So again, this inhomogeneous differential equation can be readily solved by the method of variation of parameters. So y is equal to exponential of 3x. 3 comes from negative 3x comes from here, and exponential of 3x and this function. This is a bit tedious integral, but it's doable. And the result should be, you should check this, negative 7 over 50 cosine x plus 1 over 50 sine x. And so this is a special solution. And what we need to do is to add the general solution of the homogeneous equation. So homogeneous equation is, let's see, negative d 3 d minus 2 y equal to 0. So this is the homogeneous differential equation, and we know the general solution of this is given by this. Let's write it as this one, y, some constant. Solution of this first order equation would be a exponential of negative 3x and some constant exponential of 2x. 2 comes from here. So we add this to have the general solution. So the general solution is this thing. Let's see, let's just copy it. Copy, paste, paste, and plus ae negative 3x and be 2x. So this is the general solution. And we're done. Okay, next let's consider the case when the polynomial is quadratic. T squared plus at plus b, and if factorized, it may have something like this: t minus alpha, t minus beta, and here we assume that alpha is not equal to beta, so the solution is not redundant. Note that these alpha and beta may be complex. So if the discriminant of this quadratic form, that is a squared minus 4b, if this is less than 0, if this is negative, then alpha and beta are complex numbers in general, or they may include non-zero imaginary part. And alpha and beta are complex conjugate of each other. Anyway, there's nothing special about this form of differential operator, and now we try to solve this differential equation where q of x is not 0. And okay, so this operator is factorized in this way. So we have d minus alpha and d minus beta y equal to q of x. Okay, and let this part be z. So we have d minus alpha z and q of x. Now let's solve this inhomogeneous differential equation. And to do so, we first solve the homogeneous version. Okay, and from this we can immediately see that z is equal to some constant times exponential of alpha x. And now regarding a as a function of x, then differentiate both sides of this, and we have a prime this and plus alpha a exponential of alpha x, but this part is equal to z, right? So this one. So we have a prime alpha x and alpha z. Okay. So we have this minus alpha z equal to a prime exponential of this. But from the original inhomogeneous differential equation, this should be equal to q of x. So we have a prime equal to, so divide both sides by this, so we have exponential of negative alpha x q of x. And now integrate both sides by x. We have a of x equal to integral of this. So this is just exactly how we derived the method of variation of parameters. And we substitute this function into here. Okay, so z is a x exponential of alpha x, and that is, so just swap the order, and alpha x and this. Okay, now we solve, wait, where is it? So this differential equation, okay? So the definition of z was this, d minus beta y equal to z. Okay, now let's forget about this one for the moment and just treat this z as just a function, given function. Okay, to solve this inhomogeneous differential equation, we first solve the homogeneous case. From this, we have y equals to some constant times exponential of beta x. Now then we regard this b as a function of x and differentiate y. We have b prime bx and beta b exponential of beta x. And by substituting this into here, we should have b prime exponential of beta x equal to this c. Okay, therefore b prime is equal to exponential of negative beta x times z, and integrating both sides, we have b equals to integral of this. Okay, now at this point, let's substitute this z of x by this function here. So that is exponential of negative beta and exponential of alpha x and a of x dx. And to this, we apply integration by parts, and then, okay, so we can combine these two first. So we have exponential of alpha minus beta x, a of x dx. Okay, and by exponential integration by parts, let's see. So first integrate by this, and we are assuming alpha is not equal to beta, so it's okay to divide by alpha minus beta, and exponential of this times a of x and minus, maybe we should put one of this here, and exponential of this and a prime here. And this a prime is equal to this. A prime is equal to this, so let's use that. And okay, so 1 minus beta, alpha minus beta, and alpha minus beta x, and what was it? Let's see, exponential of negative alpha x times q of x. Exponential of negative alpha x times q of x. So this part, this alpha x and this alpha x are cancelled. So after all, we have this. Let's use this a of x, replace that by this one. So that is this exponential of, what is it? Exponential of negative alpha x and q of x dx. And this one. And exponential of beta x and q of x dx. So this is the function b of x. Okay. So after all, the final solution should be, special solution should be of this form. So that means y is equal to b of x times exponential of beta x. So multiply this factor to this, everything here, and we have, so this beta x should cancel this beta x here, and exponential of alpha x, alpha minus beta, and negative alpha x, q of x dx. Let's swap this order so that we can cancel this negative sign here, and multiply by this beta minus alpha, and q of x dx. So this is the solution, the special solution of this, of that differential equation. And you should note that this solution here is symmetric regarding alpha and beta. So if we swap alpha and beta, we still get the same solution. That is understandable uh, because there's no priority between alpha and beta, and this differential equation is equal to this differential equation, this differential operator. So we can just swap the order, and there's no difference between them. So it should be, this form is expected actually. Okay, let's see an example. Let's solve this differential equation. Y double prime plus y equal to 1 over cosine x. Okay, so the polynomial in this case is t squared plus 1, which can be factorized as t minus I and t plus I. Of course, I is the imaginary unit. Okay, so just applying this formula, we have the special solution. That is, okay, so in this case, alpha would be I and beta would be negative I, okay? So if we apply this, we have exponential of ix over, so this minus this is 2I, and integral of exponential of negative I over cosine x dx, and plus, and the other part, that is negative 2I, and exponential of ix over cosine x dx. Okay, so let's consider this integral. So this is a special solution. Anyway, so let's see. To integrate this one, we first use Euler's formula. So this is cosine x minus I sine x over cosine x. And this is equal to, so cosine x, we have just 1, and sine x over cosine x. So this is just x, and negative sine x is the derivative of cosine x. So here, okay, so here we see so negative sign here. We see cosine x prime over cosine x here. So we can use the chain rule and integration by substitution, and this should be, so this I remains, and natural logarithm of absolute value of cosine x. And similarly, we can calculate this integral, and that should be just almost the same result, but different sign here. Okay. So after performing these integrations, then we have the special solution as this. So exponential of ix over 2I x plus I log cos x, and plus exponential of negative ix negative 2I and x minus I log cos x. But of course, we need to add the general solution of the homogeneous differential equation, and that is, let's write capital Y for the general solution of the homogeneous equation, and that will be C1 exponential of ix and C2 exponential of negative ix, right? So these are very easy. So just add them to find, let's call it y0 for the special solution, and the general solution is y is equal to this plus, so this can be factorized, I think, and 2I and x plus and I log cos x plus C1 minus this minus I log cos x plus C2. Okay, C2 may include I, so we don't care about the difference in some multiplication factor. So this is the general solution. But of course, this apparently includes imaginary units. So this is a complex function, a complex valued function. But if we use Euler's formula to apply Euler's formula to these factors, then this is just cosine x plus I sine x, and this is cosine minus I sine x. Then this can be written as Let's see. So there will be cosine times this part and cosine minus cosine times this part. So let's see, cosine x times, let's see, x, okay, so 2i is here. Okay, 2i is here, but so this x and this x are cancelled. Okay, so because of this negative sign. And here we have I here, and we have negative I here, so they remain. And this I is cancelled. So that is, this is same, so this 2 is also cancelled, so log of cosine x. And this C1 and C2 can be any constant, so just leave it like this, but we may redefine this. Okay, and the sine part, sine x. So for the sine part, this is positive I sine x, and this is negative I sine x that will appear. So this negative sign will be inverted, and this x remains, and we have x here. And this log part will disappear because of the negative sign here. And the constant term remains. So yeah, that should be it, I think. Let's see. Okay, let's rename this as C and D. So that it's easy to see that they are different constants. So yeah, this is the general solution. Another expression of the general solution, which can be real if C and D are real numbers, real constants. So if this and this are reals, then this function is a real valued function. All right, finally, let's consider the differential equation of this form. So d minus alpha squared y equal to q of x. So this alpha is a redundant solution of this quadratic form. And in the case of the homogeneous case, homogeneous equations, then we had some special formula for this kind of differential equation. But for inhomogeneous case, there's nothing special. So we just solve this as if this is just an iteration of the same first order differential operator. So first this and then this. Okay, so first let's define y1 as d minus alpha y. Okay, then we have d minus alpha y1 equal to q of x. So this is solved as usual. So this will be alpha x and negative alpha x and q of x dx. And next we solve this equation. So d minus alpha, let's say y2, so that's the final solution, and equal to y1. And this is of course solved readily as, so just same formula, alpha x and negative alpha x here, and instead of q we have y1 here. So this is the final solution of the special solution of this equation. And from this you can easily see that we can in general solve this type of differential equation iteratively. So this m can be any natural number. So So first we solve for y1 and then solve for y2 based on the result of y1, and you can guess that ym should be given as this. So it's like inductively we can solve this equation ym minus 1 dx. And for convenience, we may set y0 of x equal to q of x. Then, this m can be from for m equal to 1, 2, 3, and so on. And when m is equal to 1, this is y0, which is equal to q of x. So this is an inductive way to solve this differential equation. And here's an example. Let's solve y double prime minus 4y prime plus 4y equals to cosine x. And for this one, the left hand side, it's d minus 2 to the power of 2 and y. So we apply this approach, so twice, and also we should add the general solution of the homogeneous case, and the final solution should be, and you should check, should be this, 3 over 25 cosine x minus 4 over 25 sine x plus a exponential 2x and b exponential 2x. Wait a minute. So for the homogeneous case, it's not this. So it should be another x here, 2x. Well, this x is necessary because the solution is redundant here. Okay, that's all for this video. See you later.